So, hello. Today for our first Pheno-Talk. The Pheno-Talk webinar series is about smart farming, the challenges for the industrial utilization of phenotyping sensors. And what is the aim of the webinar? In the Fraunhofer webinar series, we would like to discuss what is like the challenge for bringing a phenotyping sensor, an advanced sensor, from a prototype state into an industrial utilization with various stakeholders from industry and university. So just a short introduction of myself. I'm Stefan Gerth, the head of department at the Fraunhofer-IIS and a chair of the working group Advanced Sensor Applications within the IPPN. And therefore, this webinar series is also hosted by Fraunhofer EZRT and the IPPN. So today, just as a short housekeeping, so please have in mind or do an active participation, ask any questions to the current speaker. At the top right, you should see a Q&A section. Please know all of the questions are moderated and the stream is delayed by some minutes. So we will try to answer all the questions either at the end of the talk or directly via chat. So share the information, participate actively if you want, and afterwards reach out to us or to the speaker directly if you have further questions and you don't want to discuss them here in the stream. And of course, be polite and respect confidential nature of some projects and technology. And therefore, not all questions, if they are going in that kind of directions, will be answered. But yeah, we are looking forward for having a nice webinar series all together. Just more housekeeping. Here at the link you registered, you find also the next list of speakers. We are trying to maintain a schedule for roughly every 4 weeks, having a webinar series. Then during the summertime, we will have a short break, and the wintertime proceed with this series. So our first speaker will be Bas van Aert, director of Pheno-Key, and the title of his talk is The Journey in Bringing Advanced X-ray CT Technology from Lab Concept to Industry Ready. And by himself, he's a mechanical engineer by training and started 20 years ago the professional career in horticulture automation. Since 10 years, he specialized in the automated phenotyping and process automation for crop science and in the breeding domain. And 8 years ago, he founded the company Pheno-Key to facilitate crop science organization in the process of automation and digitization, and is working now also as an independent design architect for turnkey ready systems. By himself, he's living in the heart of the horticulture industry, the Westland in the Netherlands, and I'm very happy that he's now starting this webinar series. So welcome, Bas van Aert.
Thank you, Stefan, for the nice introduction. I think my screen is now live and you can all see my presentation. Or not? No, just one sec. Now you should be able to see my presentation, I would think. Yeah. Okay. Thanks for the nice introduction, Stefan. Thank you very much, Fraunhofer, for the invitation to talk here today. And as introduced by Stefan, the next 30 minutes, I would like to share our experiences in the journey we had with Fraunhofer and have with Fraunhofer-IIS in bringing the CT technology from a first lab concept into industry-ready applications. So the topics of today will first be a broad introduction to the X-ray CT possibilities, potential applications on plants. And as mentioned, I would like to take you with me on the journey that we had for bringing the X-ray CT to industrial readiness. And what I will try to do is to touch upon multiple user perspectives, so end user perspective, engineering perspective, but also a management perspective. So here are the topics: the technology, the collaboration, and how we think, or how we did bridge the gap in the past years together with Fraunhofer. As a short introduction, I'd like to tell something about Pheno-Key. As indicated, we are design architects and system integrators by nature. We are actively doing this exclusively in the domain of plant research, crop protection, and breeding. We do this from the Netherlands. And our core competencies essentially are interdisciplinary system design, international and interdisciplinary project management. We basically operate globally, and we specialize in doing turnkey system integration and support. So we are used to integrating multiple subsystems into complete and integral systems and/or complete facilities where needed. A little bit of background about Fraunhofer, and please correct me if I make a mistake, Stefan or colleagues. So we are working together with a small part of the large Fraunhofer-Institut. So Fraunhofer comprises of multiple institutes, of which Fraunhofer-IIS is one, and within Fraunhofer-IIS there's the EZRT division, and that's focusing on X-ray development essentially. So that's the team from Stefan and colleagues, and they operate from Fürth near Nuremberg. Here you see a nice image of their impressive facility with a whole lot of toys for testing and developing new X-ray technologies. It has been established in 1998, and the facility that you see was established in 2013. In total, there are 120 employees working at 4 locations, and the 2019 budget was 20 million euros. Some interesting things: if you have the opportunity, visit them and take a tour on X-ray technology. That's very cool and very educative to do. There are multiple test setups for doing very small measurements on X-ray up to the extremely large measurements of full cars and helicopters and other cool stuff in this large theater-sized bunker on the left. I'd like to start off with some basic backgrounds of X-ray imaging, because it's a bit of a different beast in compared to the other phenotyping technologies that you might be exposed to. As the word says, it contains out of X-rays that are generated in an X-ray source, and what you see on the left here, and it sends the radiation just through the object, in this case a pot. The characteristics of the object, the density and the mass, will determine the response to X-rays, and at the back a detector will catch the remaining X-rays and will convert that into a digital signal, which can then be made visible by us by means of a 2D image. So that's the basic principle of X-ray. This talk will focus predominantly on X-ray CT, and the difference between normal X-ray and X-ray CT is that in CT imaging, 3D objects are being created by making a high number of 2D projections of different orientations of the object. So what you see here is the object will be slowly rotating between the source and the detector. Typically, far more than 1,000 projections are being captured for making creating one 3D volume. So after the collection of the individual 2D images, the 3D volume is being reconstructed by means of automated reconstruction. And then from that, the objects of interest can be segmented out by means of the smart software and algorithms and networks developed by Fraunhofer. All this is, of course, really cool when you try to apply it in the plant domain. It's the only sensor that's available at the moment that really sees through the objects, and that creates a whole lot of new applications that we're very enthusiastic about, and what's basically the driving force behind all the activities that we are undertaking and have undertaken in the past years. Just a few examples: we can make roots visible in soil-filled pots. You can do biomass measurements, seed quality measurements. You can review hidden properties, so you can imagine grains hidden within a plant. And on top of the making invisible things visible, you can always also do this at very high resolution. So between 20 and 100 micron are typically typical operating resolutions. And at the same time, it's non-destructive, and that makes the big difference in making the invisible parts visible, that you can do it repetitively without interfering with plant growth. Just a few slides that show some of the capabilities. All credits go to Fraunhofer, of course, for making this possible. So here you see one of the first applications that was focused on storage roots and tumors in soil-filled pots. And this can be used to, of course, make these objects visible, but at the same time, because of its non-destructive nature, it can also be done in time series. So that can help you to, as you can see here with the potatoes, to track the development of plant organs over time, which otherwise prior to the X-ray era could only be done by destructive measurements, by just digging up the plants and taking a look at it. Another cool one, a very famous one, of course, is the root imaging. So here you can see 3D examples of 3D root systems that can be extracted from soil-filled pots. The pots can be filled with all different kinds of soils, with different crop types, etc. And this can all be done, again, non-destructively and can yield interesting true trait parameters like length, biomass, root diameter, root angle, root density, and also soil-air interfaces. And of course, everything in 3D, which is, I think, added value in compared to other root imaging methods. An unknown area of application that is very promising in our idea is the above ground imaging. So what you see on the right side is an example of a tomato plant, which if you would see it in nature just in front of you, then you would not be able to see the tomatoes because they are all covered by leaves. You can still see the fake grayish position of the leaves. But what's possible with X-ray, you can simply see through it and really focus on the architecture of the plant or the fruits or the seeds or whatever is developing. And you can imagine that opens a lot of new doors for simple biomass measurements, but also for all sorts of new and exciting architectural measurements to characterize the development of plants. This is also a nice one that has been implemented a few times across the globe. It's for wheat ear imaging. So it's possible to, with X-ray, to measure non-destructively wheat ears that are harvested but not yet threshed, or maybe even still on plants in extreme scenarios. And within the wheat ears, make the segment the individual seeds from that and calculate various interesting traits from the seeds, still without destructing the seeds. So they remain usable for other applications, and you can imagine that opens some interesting new options in breeding processes. So the collaboration between Fraunhofer and Pheno-Talks, I think it goes back since 2015, 2014 approximately. It all started on a conference, a phenotyping conference. So that's where many things start, I think, in this domain. So there, Stefan Gerth and myself, we met up in front of Stefan's poster on X-ray imaging on potato tubers. And there, sort of the spark on sharing the interest in the technology and seeing the potential for this in the application on plants just grew, and we started to meet up, get acquainted on organization level, and from there things started growing. So I think we are now years later, and we are still going strong and every time going stronger. And I think it's safe to say, but Stefan, please let me know if you agree, that we have a very strong and mutually beneficial collaboration that has yielded many nice projects, collaborations, and technical developments. The shift of roles is that Fraunhofer is key in the technology development and the scientific collaborations to validate the technologies and to develop new technologies, and Pheno is focused on the system integration and the overall project management to help to bring this technology into real-world applications. Words are nice, but images are nicer. So here are a few slides that indicate some of the highlights of our collaborations in the past year. So we have been fortunate to be able to implement many systems on different continents across the world. In this talk, I can only comment on things we did in the academia sphere. I will not comment on things we did in the commercial organizations. But here you see a few examples in North America, Australia, and China that we have achieved over the past years. But also, probably not many of you know, is that Pheno also works together closely with Fraunhofer on the manufacturing, commercialization, and delivery of the portable X-ray units. So here you see the CD Portable, which is a device that has been originally developed by Fraunhofer, and in the meantime, Pheno has a license to sell and to manufacture this unit. So we sort of help there to take the next step with this technology in manufacturing as well. And this, for instance, has been used for retail scanning as well, but also in completely other domains. I think also something we're proud of is the establishment of the testing facility in-house at Fraunhofer in Fürth. So this is an X-ray shielded bunker essentially that has been retrofitted as climate chamber and is fitted with the latest and the greatest with respect to X-ray imaging, and also has a plant conveyor system with irrigation methods as such that Fraunhofer can conduct longer in-house experiments and even keep the plants alive while doing so. So that was also, I think, a highlight in our collaboration. There are also some activities on the field. That's still ongoing work, but I think Fraunhofer has presented a few times on this. So this is the projects to try to see how we can deploy X-ray in field situations. And what has been tested and proven is that you can measure certain biomass characteristics on shoot and also on harvest index on, for instance, wheat. Again, non-destructively and dynamically over time. So that's also a nice example of the collaboration that we have established. And a recent one that we are still growing together is the collaboration with the company Phenolytics from Germany, and they have co-developed this technology or developed this technology with the breeder Struve and also with Fraunhofer, and are now commercializing this technology. And with Phenolytics together, we are commercializing this and also bringing this to the market. And these are really cool technologies for doing seed quality testing and germination testing in 4D that otherwise have not been possible to automate it in this way. And also, very importantly, we had some fun and have some fun in the process. So here you see a few snapshots of the nice things we were able to do together in the past years. And we even established a new type of safety devices, which are the wooden shoes. If you work together with Dutch people, then at some point you will end up wearing wooden shoes. And in this case, it was to celebrate the completion of a joint project. Okay, so this was the introduction to who we are and our collaboration with Fraunhofer. The essence of the talk is to share with you how we jointly have brought the X-ray technology from first application in the lab, which you see in these slides, into the projects that you have seen in the other slides. This is literally how things started. So this is a picture in one of the testing cabins at Fraunhofer. And here you see a prototype set up with an X-ray source, a plant on a turntable, and an X-ray detector. And at the right side, you also see that the sample exchange and the caretaking of the plants all had to be done manually. The person intently looking at the plant is not an integral part of the technical design, but that's just for your information. And that was the starting point, and this is where we are right now. it's accelerated movie, but here you see that we now are at the point where sample exchange can be fully automated, scanning can be fully automated, integration within an automated system with fully automated protocols for scanning, data analysis, and data visualization. So you can imagine that that has been quite a journey, and we will zoom in onto some of the aspects of this journey. This, by the way, is at Purdue University in North America. So if we talk about the gap, so how to bridge a gap between concept development and industrial deployment, what are we talking about? What does it mean? So if you look at the extreme sides of this example, then it starts with an in-house development at Fraunhofer with limited use cases. It was primarily used as a proof of concept. It was in a dedicated X-ray bunker with walls of a meter thick. The samples had to be exchanged manually. The data processing was only semi-automated. It used a lot of manual parameterization and walking around with large data volumes. Parameterization had to be done manual. Metadata relevant for experiments had to be added manually. And of course, you can imagine that the users were highly trained X-ray professionals that operated these systems. It goes without saying that's not enough to deploy it at clients. So the current state is that systems are deployed on different continents. The use cases have been further developed, so there's more flexibility, but also more definition of what's possible and what not. More measurements can be done. The application takes place in a self-contained X-ray shielded housing. The sample exchange, if you could see, is completely automated. Same applies to the data processing and the parameterization of the processing and the acquisition and the metadata integration. And also the system is made suitable for still skilled work users, but not on the expert level as Fraunhofer to operate these systems in normal practices. So to bring a system to overall system readiness, it's not just a matter of technical things. You also have to make sure that the application is suitable for application in industry, that the integration with subsystems is ready, that the user is properly trained and prepared to work with these kinds of technologies, and of course also markets have to be developed, but that will be outside of the scope of today. So here we show that there are many different aspects that play a role to bridge the set gap in this deployment. What's also good to know is that we have experienced that the gap or the user requirements in the end can be different depending on who is your user. So this is basically the route that we have followed. It started with concept development, and then the first application was in basic research. Then we moved to applied research, and then onwards to industrial screening. And we hope in the future to really go to industrial production. So what you see is that initially it's all about making sure it works, and it doesn't need to go fast. It doesn't need to be flexible. There's no automation needed, but the moment that you start deploying things at clients, then other things become important. But we also see that, for instance, in basic research that often take place in academia, that there people are they do not want to have a very rigid and robust solution that people want in industry. They rather have a more flexible solution in which you can interact on multiple aspects and play around with certain settings to experiment. But you see, the more you get towards applied research and industrial screening, the more important robustness and throughput and end-to-end automation becomes, because those users don't want to be bothered with parameterization or manual checking of images or doing other things in a manual way. They require high-end automation and end-to-end solutions with high performance. And the same applies for the emphasis on technical support and maintenance. It becomes more and more mission critical the more you get to the industrial applications. There are a few key elements that we would like to highlight. Of course, and we focus mostly on some of the technical aspects. We want to start with safety, system integration, data management, and application definition. Safety is of course very important, especially when you talk about X-ray. It is a bit scary for some people because you've heard about X-ray. Yeah, it's not healthy for you, and you should not be exposed to too much radiation, which is of course all true. So therefore, we have to make sure that there's an intrinsic safe solution that can be safely deployed at clients. So first step in that process is to develop a radiation shielded housing, meaning a lead shielded compartment in which the full process of X-ray imaging takes place. That compartment should prevent any kind of X-rays from being sent to the outside world. And of course, those are things that are thoroughly checked in the implementation process. On top of that, because it's not a closed box that always stays closed, you need to move samples in and out. That means that you need a door, and in which the seal of radiation shielding is broken, technically speaking. So there we also had to ensure that there are interlocking systems in place that in case the doors open, that it's not possible to that the radiation is emitted through the in the space, so that the X-ray source is contained in that manner. And there are multiple of those systems, so that has been an important element of the development process. On top of the X-ray safety, machine safety is always important, but especially important for some elements related to X-ray. So you have to make sure that your radiation protocols are in order, which was mentioned in the previous slide. But also in the case of Europe, you have to deal with CE compliance to ensure that you have an intrinsically safe machine, and in which also unsafe use can be prevented. To give you a few examples, the system that you see over here, it's lead shielded as mentioned. That means the doors are also lead shielded. The doors weigh a few 100 kilograms, and you want to open and close them in such a way that you can minimize the exchange time. So you have to be very cautious on what can happen there and prevent that people can get injured. In case something happens, you want to be able to have an emergency stop, which has to be integrated with the whole system. And in the case of X-ray, there's an additional challenge that in case that someone crawls into the system, intended or unintended, it should be possible to also stop the system from there. That is different from normal imaging systems where you can only be exposed to a flash of light or something. Here with X-ray, it's a bit more dangerous. So there you also have to carefully think about how to do that. And the same applies for the controls of the system. So you have to constantly think about how can we prevent that unsafe situations can occur or can be created, and how to mitigate this in such a way that it can also not be abused. And at the same time, you also see fences around the unit to prevent that people crawl into the unit or get their hands crushed. You also have to respect that the system needs to be accessible for maintenance. So you also have to think about how can we remove those fences in those cases, but in a safe way that it cannot cannot create unsafe situations at the same time. Client education on safety is important. So safety trainings are typical, and also guiding the client through the process of getting an operating license. Train the user how to use the system in normal situations, but also how to deal with troubleshooting. And depending on the continent in which you're active, you also potentially have to deal with different controlling bodies that want to review the design of the system to ensure that everything is safe. Another aspect is the system integration itself. So the system, as you have seen, are typically integrated within an automated facility, and it has to be integrated with various levels of software, and it also has to be installed on site. So inside the lead shielded box, there's a lot of things going on. So there's the measurement setup containing all the X-ray components, but there's also, in this case, a conveyor system that moves the plant in and out of the cabinet and ensures that the plant is exactly positioned on top of a high precision rotation table to ensure that there's a good co-registration of the acquisition of the data and the angle of rotation. with an additional challenge that because the doors have to be entirely closed, there is a sort of a gap between the conveyors that have to be crossed without the plant falling over. So that those are also some challenges that we had to tackle in this process. And at the same time, you have to ensure that the plant is not harmed and is not obstructed by technical elements, and that you have a reliable and robust method of working. The software integration is, of course, also a very important element. And here we are talking predominantly about the communication that's needed to operate the system. And this representation indicates the amount of different interfaces that are needed to get to an operational situation. It's comes from practice, but there can be deviations, of course, in different scenarios. So within the X-ray, there are different software interfaces that need to work. Everything has to work seamlessly together. Also, the X-ray system has to communicate with the automated system, with the hardware components, with the PLC components, but also with the Mascada supervisory software that controls everything and is sort of the officer in charge of metadata. But that's all within the system, and to the outside world, so essentially to the client environment. Of course, the client wants to see the data, and the client also wants to dictate certain metadata that should be taken into account for doing analysis and for proper file naming, etc. So those are all interface points that you need to tackle. And the most challenging in most cases is to establish the possibility for creating remote support to support the clients in case of issues. What's also special about X-ray integration is that, again, because for lead shielded cabinet, they tend to be a bit heavy, but so to ensure radiation shielding integrity, you have to manufacture it in one piece and also ship it in one piece. So you cannot do any kind of assembly on location because that would break the seal of radiation shielding. So that means that you have to bring the entire unit to different locations in the process. So first starts with Fraunhofer, and then we want to test it at the automation supplier to make sure before we ship it that's okay. And then it has to be moved into the client's location, which, because of the size, which you see here, a relatively large size unit, which weighs maybe 8 or 10,000 kilos, can also be quite a challenge that you have to overcome to deploy these kinds of systems. So here you see that the streets had to be blocked, big equipment was needed, parts of the door had to be removed to ensure that it could be safely and intact moved indoor. If that was not enough, then this is another project where we also had to partly demolish the greenhouse. At the same time, this was in Australia during the corona pandemic. So we were responsible for the move-in of the unit, but we could not be physically there. So to facilitate this, we supervised the entire process remotely, or I have to say my colleague Ronald did this during the night from the office, coordinating with local hoisting companies to ensure a smooth and safe move-in. But then one of the most important elements is the data management and data analysis. So you can imagine when you want to deploy advanced sensors in phenotyping in real-world situations, it's not about collecting data, it's about converting that data into actionable intelligence. So that's also something that Fraunhofer is very active in and very focused on. They really want to bring it from data into basically decision-ready information, and that's also a process that has to be resolved before you can safely deploy these kinds of equipment in industrial environments. To give you an impression of the specific challenges related to X-ray, let's say we can make a scan every 10 minutes. Every scan is 40 gigabytes of raw data. After reconstruction, this amount doubles, and then is again being reduced to 3 gigabytes of data to present the final results. So you can imagine that this is a whole different beast than other types of phenotyping sensors. And that creates multiple challenges. To give you an example, if you would scan 8 hours a day, then per year, using above metrics, that would result in 1.5 petabytes of data. So those are enormous amounts for which everyone thinks they're ready, but in practice they are not ready. And that's something that that Fraunhofer identified, that a solution needs to be delivered together with this machine to be able to deliver an industry-ready machine. What does it mean? So that the entire process from acquisition and on-premise database-driven processing, it's called e-resourcing, should be automated and is automated in the meantime. That starts with automated linking of metadata to the acquisition process to instruct the sensor to which parameters to use to acquire the data, but also which parameters to use for the processing of the data. Then that can be used to use the proper templates for both the acquisition and the processing. But because of the huge amounts of data and also the computing intense nature of working with X-ray data, this has to be parallelized. Sorry. To make sure that the data processing can continue and is not interfering with the acquisition, because it's already time intensive, so you don't want to have additional delays due to waiting for processing jobs to be finished. And this is also something you want to do not in your business network, because the amount of data that you transfer over your network is huge. So there you also have to make sure that we're not causing any kind of latency problems for our clients. So that results in a database-driven process that manages all these processes. And in the end, you need multiple connected high-performance devices, each containing multiple GPUs, to enable this automated process. So this by itself is a critical task to bring it from concept development to industrial deployment. And here also the decision was made that we should offer this as an integral part to this equipment to ensure that it can deliver and does not clog up existing IT infrastructure. And next to that, you also need to integrate the entire solution with the client infrastructure, which can be, so of course the client can have access to all data, the raw data, the reconstructed data, and the segmented data. There, the discussion is, what do you want? Because again, it's a lot of data, and sometimes it's better to not store everything, but only the outputs. So data management, I cannot overstate how important this is, and also big kudos to Fraunhofer for how they have solved this in a really robust and professional manner. Also on application side, there's work to do. So literally it goes from a situation of, yay, we can see roots in our lab, to, okay, but now if you're dealing with industry, then you have to be really strict on what you can deliver, how fast, with what resolution, and what kind of performance you can achieve. And also that is a learning curve that you have to experience together. So the client wants to have a certain resolution, a certain throughput, or a certain type of measurements. And but the commitment to whether or not we can offer that combination of requirements really depends on many interconnected variables. Which crop are we talking about? Which developmental stage, or from which to what stage? What pot type? What soil mixture? What are the moisture levels in the pots? And what's the experimental protocol that you want to follow? So this is also very important to understand this together, that you know what the boundaries are, what's possible, what's not, and also to make sure that the expectations that we create with the clients, that that's realistic, can be validated, and also can be proven in the end. And especially with X-ray, with all these variables, it's important to know what you're doing and also have tested to the extent of that. So that was on the technology side, but also on there's, as I've shown in a few slides ago, there's way more than just technology. It's the essence to make this work, in my opinion, is collaboration. Yeah, if you look at the range of all the activities that are needed to achieve such results, I do not have the illusion that we can do it ourselves, or that Fraunhofer can do it himself or her or itself. So therefore, we strongly believe in a network-based operation where you work together. But then it's also important what we've learned is, yeah, you have to work from your own strengths and make sure that these are complementary to the strengths of your partner. And because of the extensive activities that you have to do, you need to have a focus on the long term. So one advice would be to really ensure that there is a strategic fit, that there are no potential conflicts, future conflicts on strategic misfits, because of the long duration, it will always emerge in the end, and then it could become a hurdle in further collaboration. I think there we've did proper due diligence, and yeah, and we are very confident that that's very complementary, and that there are no conflicts in that part. And so collaboration always has a formal side with contracts, etc. But in the end, it is trust. Trust is key. So our experience is that somewhere at some points in a collaboration, then you have to take the leap of faith together, and then you can write all the contracts that you have. But in the end, you should look each other in real life or virtually in the eye and say, okay, can we make this happen? I think, Stefan, you will also remember those moments that we had, and then together you have to take the leap of faith and work together to make it work. Also our experience is that the collaboration starts between persons, but in the end it's critical that it's carried out by the organization over its full width, so that everyone has the same mindset, everyone is aware of what the importance of the collaboration is, what the long-term goal is, and that's also a way to make it work in practice. And this is more of an overall item, but there are always differences when you work together. So if you take the Fraunhofer Pheno-Talks example, Fraunhofer is a huge organization, Pheno-Talks is a relatively small organization. There you have to respect the differences that there are, try to learn how you can use it to your benefit. Also, there can be cultural differences. The Dutch tend to be a bit direct, and so it's important that you understand it from each other, and to better understand each other. And there are many different aspects that are soft elements, as we call them, but that we also see as an important item to do a collaboration like this. That said, this is what we wanted to share today. I would like to thank Team Fraunhofer for the great collaboration and for the teamwork that we have experienced. It's great fun, and there's much more to do in the future that we are already working on, and we are looking forward to continue building on top of this. And I would like to thank you all for your attention, and would like to know if there are any further questions or discussions that you would like to engage in.
So thank you, Bas, for your talk and highlighting all the different aspects or different challenges you've seen bringing from our first prototype the system down to industry use. And in the meantime, we've collected quite a lot of questions. However, first I would like to thank you also for using this example to describe what kind of challenges you see. So the first question we've received was, in using EZRT for plants on the roots, it is possible to also make root hairs visible. And just for the audience, if you on the top right see a Q&A button, you can open also all the questions and see them by yourself. By default, this is just hidden, so if you click it once, you can read through the questions and rate them with thumbs up or also comment on them. So first question, is it possible to make root hairs visible?
Would you like to take this one, Stefan?
Maybe I could take over, yeah. So for the computed tomography, it depends on the size of the object you want to scan and the resolution you're choosing. So yes, it is possible to make root hairs visible, however, not on a full-grown plant within a pot of a diameter of 20 or 40 centimeters diameter. So it depends on the scenario, and but in general, it's possible. Yeah. So
Maybe also good to say that you have sufficient testing facilities in Fur to, if there's a concrete question, that we can test it out.
So you do the advertisement better than I do, Bast. So thanks for that one. So the next question was going a bit in the same direction. Root which are very fine, like from wheat or barley, can they be detected?
Yeah, I can comment that we do have experience with wheat roots, and I think the same applies to barley. Again, here we have to learn a bit more about the entire application to give you a solid answer. But yes, there is experience with wheat roots, but if it exactly fits with what you have in mind, that would probably require some further discussions.
Okay. Then we're jumping to the next question. Does your system identify the plants having disease conditions and at which stage?
Yeah, interesting question. It depends, of course, a little bit on how the disease manifests itself. Is it in the roots, is it in the plants, or what kind of disease is it? So the obvious answer is that for sure you can detect anomalies in development of growth of both roots and plants. So we've been seeing that has been used successfully to quantify certain effects. And whether or not identify the disease itself, that will depend strongly on which disease it is and how it manifests itself. But there are also some examples of diseases that can be quantified. And at which stage, sorry for repeating the same answer. It depends again on the application. In which stage it can or cannot be detected. One thing that I would like to point out again is that if you look at above ground imaging, that occlusion is no longer or could no longer be a limitation in quantifying effects, which is the case in many other technologies. I don't know if you have anything to add to this, Stefan.
No, not really. So as soon as we're seeing structural changes, so that's the most thing we're sensitive with X-ray, we can detect or tune for deviations. However, there's no set of final algorithm for every disease. So needs to be a further evaluation of the exact application. Yep. And another question would be how compact the X-ray unit could be.
Yeah. Is my screen still shared?
Yes.
Okay. Yeah. So here's.
I don't think so. It's shared at the moment, but it will be shared hopefully soon. Yes. Now it is shared again.
Okay. Yeah. Okay. Thank you. This is an example of a portable or compact X-ray unit. We have some internal discussions always how portable we can call it, but this is around 150 to 180 kilograms. And this is roughly the size, I think 50 by 40 centimeters footprint, and you can fit it on a tabletop essentially. There are even smaller units, but there we have to look at what the sample size can be. But the unit that you see here can be used to, from the top of my mind, for scanning 4 wheat ears at the same time and segment the seeds from it.
So for the size question, maybe a short edit note. So the X-ray unit has always to be bigger than the object you want to measure because of the shielding for the outside. And therefore, it depends really on the application, how big the unit will be in the end. And if you have further questions, just go over and or contact us. Yeah. Good. The next question was about there were now 2 questions about the field applications. There was like if the robot in the field is autonomous and how safe in the field X-ray could be. So
yeah, so there's we think it can be really safe and we think it can be autonomous. but I think it's also fair to say that we're not yet at that point. So we're at the point where the focus is predominantly on the application, with ideas on how to solve the autonomy and the safety aspect. But in the end, so I think the autonomy part is not that big of a deal. The X-ray safety, there, yeah, it's a matter of developing a smart solution for that, and it should be possible. And I think the best way to illustrate it is on the airport where you screen your bags. There it also can a safe operating situation can be created while you're standing next to the X-ray scanner. So it's not that then difficult to imagine that you can also create a similar situation in the field phenotyping vehicle. At this moment in time, it's operated remotely. So we do not have an operator sitting on it. So you just control it using a remote control, which is active over a few hundred meters.
So thank you for that. And there was another question about the field systems. If we think that the field device is capable of measuring potato tubers in ridges, ridges on the field, maybe a comment from that side. We are currently in research projects evaluating how good we can measure potato tubers or bigger below ground organs, put it like in that frame, in ridges. So at the moment, that's current developing aspects. Then we have another question. If there's any particular competitor for non-invasive sensor on the market which also tracks 4D plant growth, this is much cheaper compared with the X-ray CT device. So if I see it in that way that we track 4D plant growth below ground, I would add to that, which doing it much cheaper than with an X-ray CT device.
Yeah, so I think for below ground, the answer is simple, it's no. So to my knowledge, this is the most economic and efficient method for tracking root development in 4D using X-ray. And for above ground imaging, I think the same applies, especially when you look at the quality of imaging in obstructed scenes. So I think that's or occluded scenes, sorry. I think that's the big interesting thing of X-ray. You can make the things that happen behind the leaves, you can make it visible, which is currently often a limitation of other optical measuring technologies.
Thank you. And then we have one last question as it sees. Hi Bas, thank you for the very nice talk. Of all the challenges you've experienced in this project, which was the hardest one to overcome and which was the biggest leap of faith moment?
Hi Francesco, nice hearing from you. So I think the leap of faith moment, on the business side, it was the moment where you have to sign a contract with Fraunhofer of, let's say, close to €1 million or something like that. That says, okay, I will buy this from you, and Fraunhofer cannot guarantee that it works, cannot guarantee that it will be in time, and cannot guarantee the final price point. So those are sometimes the moments when it's really important that you can look each other in the eyes, say, okay, let's do it. It will be okay. And the same applies, of course, also to the clients, that you sign the first client contract where you have to commit yourself to delivering certain aspects. So I think that's on the business side, and on the technical side. Any thoughts from your side on that, Stefan?
I would agree. So, yeah. But from the technical side, what was the biggest challenge there? Maybe.
Yeah, I think the overall integration. So that's it's the whole of sample exchange, the software integration, making sure that the protocol was robust and was working. I think that whole that was the the biggest part. And maybe my colleague Ronald, who's doing the project management for this project, he has maybe a few other examples of ensuring that a unit of 10,000 kilos of 4-meter tall can be shipped across the globe or something like that in a safe way. So I think it can also depend on who you're asking.
Okay, so thank you very much, and also thank all the participants for the nice questions. So from that point on, I think I'm looking also to the time. I would like to conclude this first webinar series. Thank you, Bas, for giving your insights to that. And I'm looking forward to the next series where we were then discussing, like, from a more or less university point of view, what the challenges are. Okay. Thank you, and have a nice afternoon or morning, depending on in which time zone you are. Bye-bye.
Thank you, everyone. Bye-bye.